In this lab, we're going to study polarimetry, where we look at stress birefringence in different types of optical elements. And here we have a white uniform light source known as a light table, and we have two different sheet polarizers. These are linear sheet polarizers, and we're going to put one polarizer down on the table, and we're going to manually rotate the other in order to observe the stress birefringence in different materials. In this light table at Precision Optical, they actually have a Lazy Susan built into there, so they can easily rotate their polarizers to observe stress birefringence in the elements that they make. So here we have the polarizers crossed, and you see no transmission, and here you have the polarizers parallel, where you get maximum transmission through the two sheet polarizers. So the way a polarimeter works, in order to measure stress birefringence, is to put an optical element in between the two polarizers. So I'm going to start with a simple lens, and this simple magnifier is a plastic magnifier, so we should see a great deal of stress birefringence. We put the polarizer in its path, we actually see a number of different colored lines, and every color represents a path of equal refractive index. They're isorefractive paths. So the magentas and the yellows that you see in there all have the same optical path length. They have the same refractive index through that region of the glass. And as I rotate this, we can examine some of the other regions of the glass, and we can see the stress birefringence throughout the medium. Plastic optics, this is a very common effect. In glass optics, we won't see this as much. So let's look at a glass lens. And here's a glass lens that's precision optic. And even as we rotate the polarizers, we don't see any color change. We see a slight change from light to dark because the polarizers are crossed, but we don't see any color change. This is an experiment you can do to even discern how much stress birefringence is in different plastic optics, but it's very difficult with glass optics because there's so little stress in glass. You can see this optical window, precision optical window, has very little, if any, noticeable color throughout its bulk. Here's a couple other glass optics. And even with this prism and some of the other refractive elements you see here, the loop magnifier and the block, we don't see any color associated with the light transmitting through there in a polarized way. But if we look at some plastic elements, you'll see they're very interesting. We can even take some plastic utensils here, and we can see that the stress-induced birefringence in the clear plastic is quite obvious. This is a small lens that came with an eyeglass repair kit, and the stress-induced birefringence is apparent in these elements that are not precision optical, but you can consider them optical because they do deal with light. They transmit light. Even a high-quality plastic lens, such as this magnifying glass, will exhibit stress birefringence. So if we put the polarizer in its path and we put it into the polarimeter, we can actually see where this plastic lens was injection molded, because the stress birefringence is so strong on this side of the optic, and the distribution of the stress around the periphery of the optic is apparent as I rotate the polarizer back and forth. Another interesting thing to look at when you're looking at stress birefringence are Fresnel lenses. Here's a plastic Fresnel lens where we can see some of the uniformity effects that went into making the Fresnel lens. So this is a Fresnel magnifier. So polarimetry is used in a number of ways to view a number of different types of optical elements, and plastics are one of the most common ways to see stress-induced birefringence, because in glass elements, such as this lens, stress-induced birefringence will not be prominent.